In 12 days, 3IATLAS will disappear behind the Sun at perihelion, and we will lose all ability to track it during the exact window when solar heating should force it to reveal its true nature. The timing is almost surgical. Yesterday's new moon erased the night sky in perfect alignment with the comet's approaching superior conjunction. Right now, 3 coronal mass ejections are hammering Earth's magnetic field as the comet races toward its closest approach, and in less than 2 weeks, during the blackout, during the only window when an object could perform a braking maneuver without detection, every telescope on Earth will be pointed uselessly at 965,000 miles of incandescent plasma. We will be blind. December will tell us if the same object emerges. But here's what we know happened before it vanished. The James Webb Space Telescope found an 8-to-1 carbon dioxide to water ratio, 6 standard deviations above every comet ever measured. The Keck Observatory mapped nickel emissions in ratios that look more like industrial alloys than primordial ice. Spacecraft at Mars photographed it on October 3rd, showing sunward biased outgassing that defies basic comet physics. The trajectory probability, 5 degrees from the ecliptic with close approaches to 3 planets, calculates to odds of 1 in 20,000, and Avi Loeb published calculations showing that if something wants to break and enter a bound solar orbit right now, hidden behind the Sun, it would be the mathematically optimal moment to do it using a solar orbit maneuver. The accumulated improbabilities have I've reached a point where dismissal requires more faith than consideration. 4 green comets arrived in October skies simultaneously. The Vera Rubin Observatory detected this object 10 days before official discovery. A preview of the dozens of interstellar visitors it will find each year starting now. Social media erupted with claims of companion objects and fragment fields traveling alongside the comet. Unverified but persistent. And Stephen Burns documented how Earth's South Atlantic magnetic anomaly expanded by the surface area of Western Europe in the 11 years leading to this moment, just as relativistic particles from the solar storms dumped into our magnetosphere, and 2 magnitude 6 earthquakes struck within hours. Something is converging, whether it is cosmic timing, observational bias, or a test we did not know we were taking. The next 48 hours of news will not age well if December's observations show a trajectory that gravity alone cannot explain. This is not speculation dressed as science. This is data that refuses to cooperate with our models, chemistry that breaks the rules, and a visitor that chose or was chosen by physics we barely understand to arrive at the exact moment when our instruments became capable of asking the right questions, but not quite capable of answering them with certainty. The disappearing act, perihelion blackout, begins. Let me set the scene for you. For months, astronomers have been watching 3IATLAS with an intensity rarely reserved for objects passing through our solar system. The James Webb Space Telescope turned its instruments toward it. The Hubble captured its teardrop-shaped coma in exquisite detail. Ground-based observatories from Chile to Hawaii tracked its every move. Spacecraft at Mars prepared to photograph it as it sailed past the red planet. This was not just scientific curiosity. This was something approaching obsession, and with good reason, every measurement, every spectrum, every image revealed something that did not fit the playbook carbon dioxide outgassing when it should have been dormant. A chemical signature that looked more like an industrial alloy than a primordial ice ball. A trajectory that threaded the needle between multiple planets with a precision that made statisticians uncomfortable. And now, just as it reaches the moment of maximum solar heating, just as its ices should sublime most violently, just as we should be learning the most about its true nature, it disappears. The geometry is simple but frustrating. 3I Atlas approach the Sun from one direction, and Earth sits on the opposite side of our star. For several weeks, the Sun itself blocks our view. No telescope on Earth or in Earth orbit can see through 965,000 miles of incandescent plasma. We're in what astronomers call superior conjunction, and it could not have come at a worse time, or perhaps, depending on your perspective, it came at exactly the right time. October 29th. That is when 3IATLAS reached perihelion, closing to within 1.36 astronomical units of the Sun. To put that in perspective, it passed closer to our star than Mars ever gets, sliding through a region of space where temperatures soar and radiation intensifies. This is the crucible. This is where comets either prove their nature or reveal something else entirely. When a comet made of primordial ice and rock encounters this kind of heat, predictable things happen. Water sublimates into steam. Frozen carbon dioxide turns directly to gas. Dust particles lift off the surface, carried by the expanding vapor. The coma, that fuzzy envelope surrounding the nucleus, grows brighter and larger. The tail stretches millions of miles behind the comet, pushed by solar wind and radiation pressure. We've seen this dance countless times. We understand the choreography. But 3IATLAS has never followed the script, and now we cannot watch its most important scene. The blackout is not total. Of course, there are other eyes in the solar system, though their view is limited. The spacecraft orbiting Mars caught glimpses as 3IATLAS passed within 0.19 astronomical units of the red planet. On October the 3rd, the European space agencies, Mars Express and ExoMars Trace gas orbiter, both turned their cameras toward the visitor, capturing images that showed a faint smudge against the background stars. These were not close-up portraits. From Mars, 3IATLAS was still nearly 19 million miles away, a dim object requiring long exposures and careful image processing. But they saw it. They confirmed it was still there, still moving, still outgassing. Nothing changed during that observation window. Whether the comet brightened or dimmed, or showed any unexpected behavior, we are still waiting to learn. The data exists somewhere in the digital archives of Mission Control, but it has not been released, not yet. And then came the solar blackout for Earth-based observers. 3IATLAS effectively ceased to exist. Radio telescopes cannot help us here. Radar cannot penetrate to planetary distances. Infrared observations are useless when your target is hidden behind an infrared furnace. We are in the dark, and we will remain in the dark until December. That is when 3IATLAS is scheduled to re-emerge on the opposite side of the Sun, continuing its hyperbolic trajectory out of the inner solar system and back toward interstellar space. December. A full month and more of uncertainty. A full month of wondering what is happening in that hidden space behind our star. Now, let me be clear about something. Superior conjunction is not unusual. It happens to planets, to spacecraft, to any object whose orbit takes it behind the Sun. From our perspective, Mars goes through superior conjunction every 26 months. Venus experiences it every year and a half. We lose contact with our Mars rovers and orbiters for weeks at a time during these periods, and we plan for it. We send commands in advance. We put systems into safe mode. We wait. It is inconvenient, but predictable. What makes this different is the object in question and the timing of events surrounding its disappearance. Consider the sequence. 3IATLAS was discovered on July 1st, 2025, by the Atlas Survey Telescope in Chile. From that moment, it became the focus of intense scrutiny. Initial observations suggested something unusual about its composition. Follow-up spectroscopy with the Keck telescopes in Hawaii revealed emissions of nickel and cyanide in ratios that did not match anything in our solar system. The James Webb Space Telescope observed it in early August and found a coma dominated by carbon dioxide, in an 8-to-1 ratio with water, the highest ever recorded in any comet, 6 standard deviations above the norm. Then came the trajectory analysis. Multiple groups calculated its orbit and realized it approached remarkably close to Venus, Mars, and Jupiter, with a cumulative probability of less than 0.005%. Its orbital plane tilted only 5 degrees from the ecliptic, another low-probability configuration. Questions multiplied faster than answers. And now, at the moment of perihelion when solar heating should force any hidden volatiles to reveal themselves, when the comet should be at its most active and most observable, it vanishes behind the sun. Coincidence, perhaps. The laws of celestial mechanics do not care about our curiosity. Orbits are what they are, determined by gravity and momentum, not by dramatic timing. 3IATLAS did not choose to reach perihelion during superior conjunction. It simply followed the path carved by its velocity and the sun's gravitational pull. But coincidences have a way of accumulating around this object, and some researchers are starting to wonder if that word still applies. There is another element to consider, one that adds a strange synchronicity to the October timeline. On October 21st, just 8 days before 3IATLAS reached perihelion, Earth experienced a new moon. For those who do not follow lunar phases closely, a new moon occurs when the moon passes between Earth and the sun, rendering it invisible to us. The side facing Earth is in shadow. The moon effectively disappears from the night sky. And on this particular new moon, something else happened. 3IATLAS reached what astronomers call superior conjunction with the sun. At nearly the same moment, the moon disappeared. The comet disappeared, both occulted by our star within hours of each other. The alignment occurred in the constellation Virgo, with the sun, moon, and 3IATLAS forming a nearly perfect line stretching across the solar system. Astrologically minded observers have made much of this. I am not an astrologer, but I can appreciate the poetry of the moment, a new beginning, a hidden visitor, a cosmic reset button, all occurring simultaneously. Some have suggested this represents a powerful, energetic moment, a convergence of celestial forces that might influence events on Earth or reveal hidden truths about the comet. I will leave such interpretations to those who find meaning in alignments. But I will note this: the timing struck even professional astronomers as noteworthy. When you spend your career analyzing orbital mechanics and celestial events, you develop an intuition for what feels statistically normal and what does not. Multiple researchers have mentioned in private conversations and public talks that the October convergence felt unusual, not impossible, not even particularly improbable when you calculate the numbers. Just unusual in a way that makes you pause and wonder if you're missing something. Now we come to the more speculative territory, the theories that have proliferated online and in certain academic corners about what might happen during this blackout period. The most prominent voice in this discussion belongs to Avi Loeb, the Harvard astrophysicist who has never shied away from controversial hypotheses. In a series of papers and blog posts throughout the summer and fall, Loeb and his collaborators have suggested that 3IATLAS could be more than a natural comet. They've proposed, cautiously and with appropriate scientific hedging, that it might represent a technological artifact, possibly even one with hostile intent under the so-called dark forest hypothesis. The idea being that intelligent civilizations remain silent to avoid detection by predators, and any probe sent to reconnoiter another system would do so covertly, disguised as a natural object. A comet, for instance. Most astronomers dismiss this idea. They point to the cometary activity, the outgassing, the coma, the spectroscopic signatures of familiar molecules like carbon dioxide, water, and cyanide. They argue that 3IATLAS fits within the parameters of a natural, albeit unusual, interstellar comet. But Loeb counters with a thought experiment. If you were designing a probe to enter another solar system undetected, how would you do it? You would give it a coating of ice and dust. You would engineer it to outgas when heated, mimicking a comet's behavior. You would choose a trajectory that appears natural, perhaps even using gravitational assists from the very planets you wish to observe. And if you wanted to change course, to break and enter a bound orbit around the Sun rather than shooting back out into interstellar space, when would you perform that maneuver during superior conjunction? Of course, when the inhabitants of the system cannot see you, when the Sun blocks their telescopes and masks any anomalous acceleration. This is where the speculation becomes both thrilling and troubling. Loeb has calculated that if 3IATLAS were to use what is called a solar Oberth maneuver, a high-thrust braking burn performed at perihelion to maximize efficiency, it could potentially adjust its trajectory during the blackout period when the comet reemerges in December. We would measure its orbit and discover it has been captured by the Sun's gravity, no longer on a hyperbolic escape trajectory, but instead on an elliptical path that keeps it in our solar system. Such a maneuver would require significant thrust, but not beyond the realm of possibility for an advanced propulsion system, and the evidence would be unmistakable. If 3IATLAS emerges from behind the Sun on a different trajectory than predicted, every alarm bell in the astronomical community would start ringing. We would know, without question, that something intervened. We would know we are not alone. We would know we are being watched. Now, before we spiral too far into speculation, let me ground us with some perspective. The vast majority of professional astronomers consider the artificial probe hypothesis extraordinarily unlikely. The evidence for 3IATLAS being a natural comet, despite its unusual properties, remains strong. Comets are diverse. Interstellar comets formed in alien planetary systems with different chemical compositions and radiation environment could easily exhibit properties we have never seen before. The carbon dioxide dominance probably indicates formation beyond the carbon dioxide frost line in its home system. The nickel emissions, perhaps the results of unique mineral compositions in the protoplanetary disk where it originated. The trajectory, rare, yes, but not impossible in a galaxy with hundreds of billions of stars. Even 0.005% probabilities will eventually occur. Occam's razor suggests the simplest explanation. A natural but exotic comet remains the most likely, but Occam's razor also cuts both ways. If we live in a universe where intelligent life exists elsewhere, and if such life develops the capability for interstellar exploration, then probes and artifacts should occasionally pass through our solar system. The statistical argument works in both directions. So, while the default assumption should always favor natural explanations, we should also remain open to evidence that might contradict those assumptions. And that is what makes the December observation so critical. When 3IATLAS reemerges from behind the Sun, multiple telescopes will be waiting. Ground-based observatories will measure its position with exquisite precision, comparing the observed trajectory to the predicted orbit calculated from pre-perihelion data. Any deviation, any unexpected change in velocity or direction, will be immediately apparent. Space-based telescopes like Hubble and Webb will examine its spectrum and brightness, looking for changes in composition or activity level. If the comet underwent a natural perihelion as expected, these observations will confirm it. The orbit will match predictions. The spectral signature will show increased outgassing from solar heating, then gradually decrease as it moves away from the Sun. Everything will make sense. But if something else happened during those hidden weeks, if a maneuver occurred or some other intervention took place, the December data will reveal it. We will see an orbit that does not match. We will see evidence of non-gravitational acceleration beyond what cometary outgassing can explain. We will see, perhaps, changes in the object's orientation or rotation rate. And if we see those things, if the evidence points unambiguously toward artificial intervention, then everything changes. The conversation shifts from academic debate to existential reckoning. We would face questions humanity has contemplated for centuries, but never had to answer with immediacy. Are we alone? Are we being studied? Are we safe? What do we do next? For now, though, we wait. We wait in a peculiar state of suspended curiosity, knowing that something significant is happening, but unable to observe it. We wait while 3IATLAS, whatever it truly is, bathes in the sun's radiation at close range, potentially undergoing transformations we cannot measure. We wait and wonder if the universe is about to reveal one of its greatest secrets, or if we're simply watching a very unusual comet do very unusual but entirely natural things. The ambiguity is maddening, the anticipation is electric, and the clock ticks toward December, when the veil will lift and we will finally see what emerges from the other side of the sun. This is the moment we find ourselves in. Not quite knowledge, not quite ignorance, somewhere in between. Suspended impossibility, waiting for the cosmos to show its hand. And while we wait, other pieces of the puzzle continue to fall into place. Other observations and coincidences that deepen the mystery rather than resolve it. The October timeline holds more surprises than just the disappearance of 3IATLAS. And those surprises have left even skeptical scientists shaking their heads in disbelief. The October cosmic convergence. Something strange was happening to Earth in mid-October, and it had nothing to do with the comet hiding behind the sun, at least not directly. Between October 16th and October 21st, our planet found itself caught in a barrage of solar activity, unlike anything we had seen in months. Multiple M-class solar flares erupted from a rapidly growing sunspot group, each one more powerful than the last three. Separate coronal mass ejections launched from the sun's surface, each carrying billions of tons of magnetized plasma across 93 million miles of space, all aimed directly at us. NOAA issued a G2 geomagnetic storm warning, then quietly upgraded their internal models as the data came in, showing the impacts might be strong, longer than anticipated. And right in the middle of this solar assault, as Earth's magnetic field buckled and flexed under the onslaught, 3IATLAS reached superior conjunction with the sun during the new moon. The timing made people nervous. Let me paint the picture more clearly. Solar flares are not unusual. Our star goes through an 11-year cycle of activity, and we are currently near solar maximum, the peak of cycle 25. During these active periods, sunspot groups form and dissipate. Magnetic field lines tangle and snap, and energy releases in spectacular bursts of radiation and charged particles. We expect this. We monitor it. We have entire agencies dedicated to space weather forecasting. But the specific sequence of events in mid-October stood out. The sunspot group that spawned the flares grew rapidly, expanding to several times the diameter of Earth within just days. It rotated into geo-effective position, meaning it faced directly toward our planet, ensuring that any eruptions would hit us square on, and it did not stop flaring. October 16th saw the first major eruption, an M-class flare that sent ultraviolet and X-ray radiation streaming toward Earth at the speed of light. Arriving 8 minutes later, radio operators noticed disruptions. Satellite controllers logged anomalies. Nothing catastrophic, but noticeable. Then came the coronal mass ejections, the slower-moving but more dangerous component of solar storms. These massive clouds of plasma take days to traverse the distance between the Sun and Earth, and forecasters tracked 3 of them, each following slightly different trajectories, but all converging on our planet within a narrow time window: October 19th, October 20th, October 21st. 3 impacts in 3 days, with the final one arriving just hours before the new moon, just hours before 3IATLAS slipped behind the solar disk. When the plasma hit, Earth's magnetosphere compressed the magnetic field lines that normally extend tens of thousands of miles into space, got pushed back toward the planet's surface. Auroras danced across the sky at unusually low latitudes, visible as far south as the northern United States and Central Europe. But the visible light show was just the surface manifestation of deeper, more significant changes Earth's radiation belts. Those donut-shaped regions of trapped high-energy particles surrounding our planet became supercharged for about a week, leading up to October 13th and 14th. The radiation belt flux remained at extraordinarily high levels, well above normal background. Then, on October 13th and 14th, something called an ion precipitation event occurred. The trapped particles suddenly dumped into the upper atmosphere, releasing their energy in a cascade that rippled through the magnetosphere, and immediately following that release, two significant earthquakes struck a magnitude 6.5 near Papua New Guinea and a magnitude 6.3 in the Drake Passage, both registering on October 16th, just as the solar activity intensified. Now, I need to be careful here. The connection between solar activity and seismic events remains controversial in mainstream geophysics. The standard view holds that earthquakes result from tectonic stress accumulation and release driven by the slow grinding of crustal plates over geological timescales. Solar storms occur on timescales of hours to days and involve electromagnetic energy, not mechanical force. There is no accepted mechanism by which a coronal mass ejection could trigger an earthquake. And yet, researchers like Stephen Burns, a geophysicist who's been tracking these correlations for years, keep finding patterns, ion precipitation events followed by major seismic releases, low solar wind density periods coinciding with upticks in high-magnitude earthquakes. It is not proof. It is not even strong evidence by scientific standards. But it is persistent enough to make you wonder if we're missing something about how energy flows through interconnected systems. The October sequence fit the pattern Burns has been documenting: supercharged radiation belts, sudden discharge, major earthquakes within hours, and then, as if on cue, another punch to the magnetosphere from the incoming coronal mass ejections, recharging the radiation belts and setting up the system for another potential release. The timing alignment with 3IATLAS superior conjunction might be meaningless. Space weather and comet orbits operate on completely different physical principles. But humans are pattern-seeking creatures, and when unusual events cluster together, we cannot help but wonder if they share a hidden connection. Then there is the magnetic field situation, which has been quietly growing stranger for years, but reached a notable milestone in October 2025. The European Space Agency released updated data from their Swarm satellite constellation, showing how Earth's magnetic field has evolved from 2014 to 2025. The results were striking. The South Atlantic anomaly, that region off the coast of Brazil where Earth's magnetic field is unusually weak, has expanded dramatically in 11 years. It has grown by an area roughly equivalent to Western Europe. The field strength in that region has dropped by 330 nanotesla, a significant decrease. At the same time, other features of the magnetic field have shifted. The flux lobe over Siberia, where the field is stronger than average, has increased by about 250 nanotesla. The flux lobe over Canada has weakened by more than 800 nanotesla. These are not trivial changes. They represent a magnetic field in flux, literally and figuratively. The South Atlantic anomaly matters because it is where Earth's protective shield is weakest. Cosmic radiation, normally deflected by the magnetic field, can penetrate deeper into the atmosphere in this region. Satellites passing through the anomaly experience higher rates of electronic glitches and failures. The International Space Station, when it passes over the anomaly, exposes astronauts to increased radiation doses, and now the anomaly is expanding eastward, reaching toward South Africa, growing in both size and intensity. It is not an immediate crisis, but it is a long-term trend that nobody fully understands. Some models suggest it could be the early stages of a magnetic pole reversal, an event that occurs every few 100,000 years on average and has not happened in 780,000 years. We are, statistically speaking, overdue. Other models suggest it is just a normal fluctuation, a wobble in the geodynamo that will eventually correct itself. Nobody knows for certain. What we do know is that during the October solar storm sequence, this weakened region of Earth's magnetic field got pummeled by charged particles. More cosmic radiation than usual made it through to the atmosphere. More energy dumped into the system. And all of this happened while the northern magnetic pole continued its steady march from Canada towards Siberia, accelerating from its historical drift rate of about 10 km per year to its current pace of roughly 40 km per year. The magnetic field is moving, the anomalies are growing, and we hit all this with 3 coronal mass ejections during the exact week that 3IATLAS disappeared behind the sun during a new moon. The coincidence is almost poetic. Some observers, particularly those attuned to energetic or metaphysical interpretations of celestial events, saw the October convergence as deeply significant. The new moon represents new beginnings, a reset, a clearing of the slate. Superior conjunction puts an object in direct alignment with the sun, theoretically amplifying its energetic influence. The constellation Virgo, where this alignment occurred, carries associations with purity, transformation, and hidden knowledge. Layer on top of that the intense solar activity, the magnetic field perturbations, the seismic releases, and you have a recipe for something that feels cosmically important, even if you cannot quite articulate why. I'm not here to validate or dismiss those interpretations. I'm here to note that multiple independent phenomena operating on different timescales and through different mechanisms all peaked in a narrow window of days in mid to late October 2025. That is a fact. What it means, if anything, remains open to interpretation. But let us return to the more concrete question. Could the solar activity have affected 3IATLAS? Could the same coronal mass ejections that battered Earth have also interacted with the comet as it passed through perihelion? The answer is yes, almost certainly. Solar storms do not just affect Earth. They propagate throughout the entire inner solar system. When a coronal mass ejection erupts from the sun, it carries with it a bubble of enhanced magnetic field and high-energy particles that expands outward at speeds of several hundred kilometers per second. As this bubble sweeps past planets, asteroids, comets, and spacecraft, it can cause measurable effects. Cometary tails get pushed around. Dust particles in a coma experience additional forces. The rate of sublimation might even change slightly as the particle flux increases. For a comet sitting at 1.36 astronomical units from the Sun during perihelion, right in the heart of the inner solar system, the October solar storms would not have been gentle. Now, would those effects be dramatic enough to notice? Would they change the comet's trajectory or reveal hidden properties? Probably not. Solar storms are energetic on human scales, but relatively weak when it comes to moving massive objects through space. 3IATLAS, even if its nucleus is only a few kilometers across, has enough mass and momentum that a coronal mass ejection would barely nudge it. The increased particle flux might enhance the coma brightness slightly or alter the dust distribution, but those are subtle effects. If the comet is natural, the October solar activity would not fundamentally change its behavior. But if the comet was something else, if it contained sensors or instruments designed to monitor its environment, those sensors would have registered the storm. An artificial probe passing through the inner solar system during a period of heightened solar activity would collect valuable data about how stars behave during their active phases. It would be an opportunity, not a threat. This brings us to an uncomfortable realization. If you were designing a mission to study another star system, you would want your probe to arrive during an active period. You would want to measure the stellar wind variations, the magnetic field fluctuations, the particle fluxes and radiation levels that any inhabited planet would experience. Arriving during solar minimum, when the stars quiet and boring, would tell you less than arriving during solar maximum, when things are dynamic and potentially hazardous to biology. And if you are really clever, you would time your perihelion passage to coincide with a period of elevated activity, maximizing the data return. The October convergence, seen through that lens, looks less like coincidence and more like planning. I'm not saying that is what happened. I'm saying the thought has crossed more than a few minds in the astronomical community, usually late at night after too much coffee, when the strange coincidences pile up and the rational explanations start to feel inadequate. We also cannot ignore the human element. The October convergence did not just affect instruments and magnetic fields, it affected people. During periods of intense solar activity, reports of disrupted sleep, heightened anxiety, and unusual dreams tend to increase. Emergency room visits for cardiac events show a slight uptick. The mechanisms remain debated, but the correlations exist in the literature. Our bodies contain iron in our blood, trace minerals in our tissues, electrical signals running through our neurons. We are electromagnetic beings living in an electromagnetic environment. When that environment shifts dramatically, we feel it, even if we do not consciously register the cause. And in mid-October, as the solar storms hit, as the magnetic field buckled, as the new moon erased the sky and 3IATLAS slipped out of view, millions of people reported feeling off, restless, uneasy, a sense that something was about to change. Maybe it was just the storms. Maybe it was collective anxiety amplified by social media. Or maybe, just maybe, we were sensing something our instruments had not yet confirmed. The geophysicist Stephen Burns captured this moment in his analysis of the period. He noted the sequence of events, the charged radiation belts, the earthquakes, the incoming high-speed solar wind stream that followed the coronal mass ejections. He observed that the new moon coincided with 3IATLAS's superior conjunction and suggested, with a mix of scientific caution and genuine wonder, that October 21st represented a powerful, energetic moment. He encouraged people to practice self-care, to spend time in nature, to rest and reflect, not because he believed in astrology or mysticism, but because he recognized that human beings respond to their environment in ways we do not fully understand, and extraordinary environmental conditions call for mindful attention. It was a remarkably grounded response to an extraordinary confluence of events. And now, as we move past that convergence point, as the solar storm subsides and the magnetic field returns to its baseline state of slow drift and quiet anomalies, we are left with questions. Did anything significant happen during those days? Did the hidden comet respond to the solar barrage in unexpected ways? Will the December observations reveal changes we cannot yet imagine? Or was October 2025 simply a statistically unusual but ultimately meaningless clustering of independent events? The kind of thing that happens occasionally in a complex, chaotic universe. We will not know until the comet reemerges. Until then, we move to the next chapter of this story, to the observations that were made before the blackout, to the spacecraft that managed to catch fleeting glimpses of our mysterious visitor as it raced past Mars and into the sun's glare. Those observations hold clues, and some of them are deeply strange. 4 spacecraft stalk the visitor. On October 3rd, 2025, while Earth prepared for the incoming solar storms, and astronomers watched 3IATLAS approach its date with the sun, a different kind of observation was taking place. 19 million miles away at Mars, an unprecedented campaign was unfolding. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter had been quietly repositioned over the preceding weeks, their cameras and spectrometers calibrated for a target. far fainter than the ruddy surface they were designed to study. NASA's Mars Reconnaissance Orbiter received similar instructions. Down on the surface, the Perseverance and Curiosity rovers tilted their Mars cameras toward the sky, programmed to attempt observations that pushed the limits of what surface-based instruments could achieve. This was not a casual effort. This was a coordinated interplanetary surveillance operation, and the target was our mysterious visitor. As it sailed past the red planet at its closest approach, the results were mixed, frustrating, and in some ways more intriguing than a clear success would have been. Mars Express and ExoMars Trace gas orbiter succeeded. They captured images faint, grainy, requiring extensive processing, but real data showing 3IATLAS against the star field. The cameras, designed to photograph a bright planet from less than 200 miles away, were instead pointed at an object 10,000 to 100,000 times fainter, sitting nearly 30 million kilometers distant. That they saw anything at all represents a technical achievement. It's worth celebrating. Nick Thomas, the principal investigator for the Cassini camera on the Trace Gas Orbiter, called the observation very challenging. In what might be the understatement of the year, the images show streaked stars and a faint smudge where the comet should be. Not glamorous, not the kind of thing you put on a poster, but scientifically valuable because it confirms position, brightness, and most importantly, continued activity. 3IATLAS was still outgassing on October 3rd. It still had a coma, it was still behaving, at least superficially like a comet, but here's where things get interesting. The images revealed something unexpected in the comet's appearance. Instead of a round symmetric coma that you might expect from a uniformly sublimating nucleus, the processed images showed the coma appeared slightly elongated with more material extending in one direction than others. Now, asymmetric comas are not unusual. Most comets show some degree of lopsidedness, because their nuclei are irregularly shaped rotating bodies with active regions concentrated in certain areas. As the nucleus rotates, different patches face the sun at different times, creating jets and plumes that push material outward in preferred directions. So the asymmetry alone is not alarming. What called attention was the specific geometry. The enhanced outgassing appeared to favor the sunward direction, which is backwards from what you typically see normally. The intense solar radiation and wind push cometary material away from the sun, creating the iconic tail that always points opposite the star, but through Atlas seemed to be puffing more material toward the sun than away from it. The Keck observations from late August had hinted at this. The sunward bias distribution of dust and gas, visible in the nickel and cyanide emission maps, suggested something unusual about how the comet responded to heating. The October images from Mars orbit confirmed the pattern persisted. Explanations exist for this behavior if the nucleus does not rotate rapidly. If it is tidally locked or tumbling slowly, the day side could remain constantly heated, while the night side stays cold and inactive. All the sublimation would occur on the sunward hemisphere, pushing material outward in that direction before the solar wind catches it and sweeps it back into a more traditional tail configuration. It is a reasonable model. It fits the data, but it also requires specific conditions, a slowly rotating nucleus, which is somewhat unusual for objects that have spent billions of years tumbling through space, subjected to every gravitational nudge and collision imaginable. Objects tend to spin freely. Atlas apparently does not spin much, or it is hiding something. The European Space Agency was cautious in their official statements. They described the observations as successful, providing valuable data on an interstellar object at a unique vantage point. They noted the faintness of the target and the technical challenges overcome. They did not speculate about the asymmetry. When pressed by journalists, ESA spokespersons emphasized that full analysis of the data was ongoing, and that preliminary interpretations should be treated as tentative. Translation: we saw something interesting, we're not sure what it means, and we're not going to stick our necks out until we have more information. This is standard scientific caution, the appropriate response when dealing with extraordinary claims and limited data. But it also left a gap, a space where speculation could flourish, and flourish it did. NASA's Mars Reconnaissance Orbiter also attempted observations around the same time, and here the story becomes murky. The spacecraft has a powerful camera called HiRISE, the High-Resolution Imaging Science Experiment, capable of resolving features on the Martian surface down to about 30 centimeters, pointed at the sky. It could theoretically capture much more detail of 3IATLAS than the European orbiters managed. NASA announced they would attempt the observation. They confirmed the spacecraft executed the pointing maneuvers, and then silence, no images released, no official statements about success or failure, no data published for the scientific community to analyze. This is not necessarily suspicious. Spacecraft operations are complex. Data processing takes time, and mission teams have priorities beyond satisfying public curiosity. But it is unusual. Typically, when a successful observation of a high-profile target occurs, NASA releases at least a preliminary image relatively quickly, capitalizing on the public interest and demonstrating the value of their mission. Mars Reconnaissance Orbiter imagery. Weeks after the observation window suggests either technical failure or something in the data that requires careful review before release. The surface rovers, Perseverance and Curiosity, faced even steeper challenges. Pointing cameras designed for close-range geology at a faint comet millions of miles away is not what those instruments were built for. The sensitivity is wrong. The exposure times are too short. The image processing pipelines optimized for rocks and soil, not distant astronomical objects. NASA stated the rovers would attempt observations, but set expectations low. To date, no results have been announced from those attempts. Most likely, the rovers simply could not detect the comet against the sky brightness and instrumental noise. But the attempt itself tells you something about how seriously the scientific community took this opportunity. They were willing to repurpose assets, to push instruments beyond their design specifications, to coordinate observations across multiple spacecraft and agencies, all for a few more data points on this enigmatic visitor. That level of effort does not happen for routine comets. The coordination speaks to something deeper, a recognition that opportunities to study interstellar objects are vanishingly rare. 3IATLAS is only the third confirmed visitor from beyond our solar system. The first one, Oumuamua, passed through in 2017 and was gone before anyone realized what they were looking at. By the time telescopes turned toward it, Oumuamua had already shot past the Sun and was racing back into interstellar space, too faint and too fast to study in detail. The second, Borisov, arrived in 2019 and gave astronomers a longer observation window. It was clearly a comet with a bright coma and obvious tail, and multiple telescopes tracked it for months. But it too left before we could answer all the questions it raised. See 2023. A3IATLAS represents the third chance, and possibly the best chance, to really understand what interstellar objects look like, how they behave, and what they can tell us about the regions of space between the stars. Every observation counts. Every data point matters. You do not waste opportunities like this, even if it means using spacecraft in unconventional ways. But there is more to the October campaign than just the Mars assets. The European Space Agency also announced that their JUICE mission, the Jupiter Icy Moons Explorer, currently en route to the outer solar system, would have an opportunity to observe the comet in November 2025. JUICE launched in 2023 and is taking a complex trajectory involving multiple gravitational assists to eventually reach Jupiter. Its path will place it in a position to observe the comet as both objects move through different regions of the solar system. The geometry is not ideal. Juice will be far from the comet, but the spacecraft carries sophisticated instruments designed for detailed compositional analysis of icy moons. Those same instruments can be turned toward a comet, and the data they collect will complement what ground-based and near-Earth space telescopes can gather. This is another piece of the multi-platform observation strategy, using every available asset to build a complete picture. And then there is the question of what comes next. If the comet survives its perihelion passage, if it reemerges in December, still intact and still active, there will be additional opportunities for spacecraft observations. The comet's trajectory will take it past Jupiter's orbit in March 2026. As it exits the inner solar system, at that distance, ground-based telescopes will struggle to track it. The object will be too faint, but spacecraft in the outer solar system might catch final glimpses. NASA's Juno mission, currently orbiting Jupiter, could potentially observe the comet if mission planners decide the science value justifies the fuel expenditure. The New Horizons spacecraft, now cruising through the Kuiper Belt after its flyby of Pluto and Arrokoth, sits too far away and pointed in the wrong direction to contribute. But the European Space Agency has floated the possibility of using existing assets in creative ways, leveraging spacecraft that were not designed for comet observations but happen to be in useful locations at useful times. This patchwork approach, using missions designed for other purposes and stretching their capabilities to study an unexpected target, highlights both the ingenuity and the limitations of current space exploration. We do not have a dedicated interstellar object interceptor sitting on standby. We do not have a rapid response mission that can launch within weeks of discovery and rendezvous with a visitor before it leaves. The proposed Comet Interceptor mission, a European Space Agency project designed to wait in space until an interesting target appears and then chase it down, remains in development and will not launch until 2029 at the earliest. For now, we make do with what we have, repurposing orbiters and rovers and deep space probes, squeezing every drop of science from instruments pointed at targets they were never meant to observe. The Mars observations, imperfect as they were, provided crucial confirmation 3IATLAS was where it was supposed to be. It was moving as predicted. It showed continued cometary activity. These are important data points because they constrain the possible explanations. A completely inert object, say a chunk of solid rock or metal, would not show a coma. An object undergoing powered flight using onboard propulsion to alter its trajectory would show up in the wrong place when telescopes looked for it. The October 3rd observations rule out those possibilities. Whatever 3IATLAS is, it interacts with sunlight in ways that produce visible outgassing. It follows a ballistic trajectory shaped by gravity, not thrust. It looks, acts, and moves like a comet, even if it is a very unusual one. But those same observations leave questions unanswered why the sun would bias in the outgassing. Why the lack of a prominent tail despite obvious activity? Why does an object that should be spinning show evidence of slow or negligible rotation? These are not for the natural comet hypothesis, but they are loose threads, details that do not quite fit the standard model. And in science, loose threads are where discoveries hide. You pull on them gently, carefully, following where they lead. Sometimes they unravel into nothing, a measurement error or a misunderstanding of the physics. Other times they unravel into something profound, a new phenomenon that forces you to rewrite the textbooks. We will not know which kind of thread we're pulling until we gather more data. And the most critical data will come when 3IATLAS reemerges in December. Until then, we have the October observations, tantalizing hints from spacecraft scattered across the inner solar system, pieces of a puzzle that remain stubbornly incomplete. And while those spacecraft were watching the comet, ground-based observers were turning their attention to a different mystery, one that made the October skies look less like a random collection of icy wanderers and more like a coordinated arrival. The October Comet Swarm. 4 green visitors. If you looked up at the night sky in October 2025, with even a modest pair of binoculars, you would have seen something unusual. 4 comets, all glowing with that characteristic greenish hue that comes from diatomic carbon emissions, all visible simultaneously in different parts of the sky. 4 frozen wanderers, all discovered within the same year, all reaching their peak brightness within days of each other. See 2025 A6 Lemon reaching closest approach to Earth on October 21st. See 2020 R2. Swan swinging within 24 million miles on October 20th. See 2025 K1 Atlas, a faint cousin discovered in May but still visible through telescopes. And of course, 3IATLAS, the interstellar visitor that captured everyone's attention. The amateur astronomy community was ecstatic. Professionals were intrigued, and on social media a question started circulating. Is this normal? Have we ever seen 4 comets in the same month before? What are the odds? The answer depends on how you frame the question. Comets are not rare at any given time. Dozens of them orbit the sun. Most too faint to see without powerful telescopes. A few bright enough to catch the public eye. Long-period comets, those with orbital periods measured in centuries or millennia, arrive from the distant Oort cloud on trajectories that bring them into the inner solar system, around the sun, and back out into the cold dark for another circuit. Jupiter family comets, with shorter periods of just a few years to a few decades, loop through the inner system more frequently. They're all bit-shaped by gravitational interactions with the giant planet. We discover several new comets every year. Surveys like ATLAS, Pan-STARRS, and now the Vera Rubin Observatory constantly scan the sky, picking up faint smudges that were not there the night before, calculating orbits, determining which ones will brighten enough to be interesting. So, having multiple comets visible at once is not extraordinary. What made October 2025 noteworthy was the timing and the brightness. In 2025, A6 Lemon was discovered on January 3rd by the 60-inch telescope at Mount Lemmon Observatory in Arizona. Early observations suggested it would remain a faint telescopic object. Interesting to comet enthusiasts, but not a public spectacle. Then, as it approached the sun throughout the summer and fall, it began brightening faster than predicted. By October, Lemon had become visible to the naked eye under dark skies, reaching magnitude 4 or possibly even brighter. For context, magnitude 4 is about the limit of what the average person can see, without optical aid in a reasonably dark location. A comet at magnitude 4 is not a stunning sky show like Hale-Bopp or Neowise, but it is noticeable. A fuzzy patch that does not belong among the familiar stars. Lemon's orbit analysis revealed it would pass within 0.6 astronomical units of Earth, close enough to appear impressively large through binoculars, showing a bright central coma and a short tail, and its orbital period, calculated from the trajectory, came out to about 1,396 years. This comet last visited the inner solar system around the year 629 during the early medieval period. It will not return until the year 3421, long after everyone reading or hearing these words is gone. A once-in-a-lifetime object, literally. See 2025 R2. Swan was discovered much more recently, on September 10th, by Ukrainian amateur astronomer Vladimir Bezugly, while analyzing images from the Swan instrument aboard the Solar and Heliospheric Observatory. Swan is not primarily a comet hunter. It measures hydrogen emissions from the solar wind and the interplanetary medium, but comets show up in its data as bright sources of hydrogen from the dissociation of water molecules. Bezugly noticed something new, calculated a rough orbit and reported it. Follow-up observations confirmed a comet on a trajectory that would bring it very close to the Sun, to 0.5 astronomical units at perihelion on September 12th, and then swing out toward Earth by mid-October. Swan had brightened to naked-eye visibility in dark skies, competing with Lemon for attention. Its orbit is also long period, suggesting a visitor from the Oort cloud, making one of its rare passages through the planetary region. 2 bright, long-period comets arriving within weeks of each other. Unusual, but not unprecedented. See 2025 K1-ATLAS. Discovered in May, represents the faint companion of the group. Never expected to reach naked-eye brightness. It has remained a telescopic object, visible only through backyard telescopes with apertures of at least 6 inches or larger. Its trajectory brings it closest to the Sun in early October, passing just inside Mercury's orbit at 0.33 astronomical units, a scorching distance where temperatures can vaporize all but the most refractory materials. Some predictions suggested K1-ATLAS might not survive that close approach, that it could fragment or disintegrate entirely, adding to the list of sun-grazing comets that meet their end in the intense heat and tidal forces near our star. As of late October, its survival remains uncertain. Observations are difficult because of its faintness and unfavorable geometry. If it did survive, it will become more visible in late November as it moves away from the Sun and into darker sky. But expectations remain modest. This is not a showstopper, it is a footnote. A curiosity for dedicated observers who like to track every new discovery. Still, it adds to the count 3 comets from our own solar system, all discovered in 2025, all reaching perihelion within months of each other. And then there is the 4th, 3IATLAS, the interstellar interloper, which never became a naked-eye object despite all the attention and all the speculation. It remained too faint for casual observation, requiring at least a small telescope and, preferably, a camera capable of long exposures to capture its feeble light. But it is there, or was there, before slipping behind the Sun, adding its presence to the October collection 4 green comets. The color comes from the same chemistry in all of them carbon compounds in the coma, breaking apart under ultraviolet radiation and fluorescing in the green part of the spectrum. Diatomic carbon. C2 molecules emit strongly at wavelengths around 515 nanometers, right in the middle of the green band that human eyes perceive easily. Nearly all comets show this green glow when they get close enough to the Sun. It is as characteristic of comet activity as the tail itself. So, the green color is not mysterious. The timing, however, started to raise eyebrows. The viral claim began circulating on social media in early October. 17 comets, all crowding the inner solar system at once, all pulling away in unison by mid-2026. A coordinated pulse of comet activity never seen before. The claim came with impressive sound. The language about rare alignments and statistical impossibilities. And it spread rapidly through conspiracy-minded communities and even some mainstream science forums. 17 comets. That number alone sounds alarming. But when you dig into the details, the picture becomes much less dramatic. Yes, there are currently about 17 known comets within the inner solar system, defined as inside Jupiter's orbit, but that is actually normal. At any given time, multiple comets loop through this region. Some are Jupiter family comets on their regular multi-year orbits. Some are long-period comets making their once-per-millennium visits. Some are newly discovered objects whose orbits we're still refining. The idea that they are all crowding in at once implies some kind of coordinated arrival, as if they were summoned or directed. The reality is that cometary orbits are continuous. Objects are always arriving, always passing through, always leaving. The apparent clustering in October 2025 results more from observational bias. We notice them because they got bright at convenient times, than from any genuine statistical anomaly. The claim that they will pull away in unison by mid-2026 is similarly misleading. Comets on different orbits do not move in lockstep. Each follows its own path, governed by its own velocity and the gravitational pull of the Sun and planets. Some of the comets currently in the inner system will leave quickly, shot out on hyperbolic trajectories or long ellipses that take them back to the Oort cloud. Others will stick around longer, orbiting Jupiter or lingering in the asteroid belt region before eventually being ejected or absorbed by impacts. There was no coordinated exodus scheduled for 2026. What you do have is a higher-than-average number of bright comets visible from Earth in the latter half of 2025, driven partly by random chance, and partly by the increasing sensitivity of sky surveys that are now discovering comets earlier and more reliably than in past decades. The Vera Rubin Observatory, which began operations in June 2025, has already revolutionized the detection rate. In just its first months of operation, it discovered over 2,000 asteroids in 10 hours of observation time. That kind of capability means we will be finding more comets. Not because more are arriving, but because we're getting better at spotting them. So, the 17-comet conspiracy deflates under scrutiny. But deflating a conspiracy does not erase the underlying sense of wonder. 4 bright green comets in the same month is still a treat for sky watchers. The fact that one of them is an interstellar visitor adds the layer of significance that transcends the statistics. And even if the clustering is not cosmically meaningful, it serves as a reminder of how dynamic the solar system remains. We tend to think of space as static, the planets and moons locked in their eternal orbits, unchanging across human lifetimes. But the solar system is full of transients, objects passing through on one-time visits, ice and rock and dust shaped by forces we barely understand, each one carrying a story written in its chemistry and trajectory. October 2025 gave us a chance to see that dynamism on display, to appreciate the ongoing churn of the cosmic environment we inhabit. Lemon and Swan will fade as they move away from Earth and the Sun, their brief moment of glory ending as they return to the obscurity of the outer solar system or the Oort cloud. K1-ATLAS, if it survived perihelion, will follow a similar path, its faint light disappearing into the background glow of the sky. And 3IATLAS will re-emerge from behind the Sun in December, continuing its journey outward, bound for interstellar space once more. Unless something unexpected happened during the blackout period. The October comet swarm, such as it was, will disperse, but it will not be forgotten. Those of us who took the time to look up, to point our binoculars or telescopes at those fuzzy green smudges, will remember the autumn when the sky was unusually full, when 4 wanderers from the cold dark graced our skies at once, and when one of them carried with it questions that still have no answers. The broader lesson here is about perception and reality. Social media amplifies patterns, turning coincidences into conspiracies, making the unusual seem impossible and the rare seem orchestrated. The 17-comet claim is a perfect example. Take a kernel of truth, 4 visible comets in October. Add some dramatic language about coordinated arrivals, and suddenly you have a story that feels significant, maybe even ominous. It taps into our desire for meaning, our tendency to see agency and intention in random events. But reality is more nuanced. Yes, October 2025 was a good month for comet watching. No, it was not unprecedented. Yes, having an interstellar visitor in the mix makes it special. No, the comets are not acting in concert. They're independent actors following the laws of physics, oblivious to each other and to our interpretations of their presence. And that, in its own way, is more beautiful than any conspiracy. The universe does not need to coordinate its wonders to impress us. It does so by simply being itself, chaotic and creative and full of surprises. But while the comet swarm captures the imagination, it is the chemistry of 3IATLAS that continues to perplex scientists. The Keck observations from late August reveal details about the comet's composition that do not fit easily into our models. And those details are where the real mystery lies: Keck's nickel cyanide asymmetry. August 24th, 2025. The twin domes of the W.M. Keck Observatory on the summit of Mauna Kea in Hawaii open to the night sky. And inside, the Keck Cosmic Web Imager prepared to observe 3IATLAS at a wavelength specifically chosen to reveal two molecules, nickel and cyanide. These are not random selections. Cyanide, in the form of CN radicals, is common in comets, a signature of organic chemistry frozen into the ice during the comet's formation. Nickel, on the other hand, is unusual. Most comets emit very little atomic nickel. When they do, it is typically accompanied by roughly equivalent amounts of iron, reflecting the cosmic abundance ratios you would expect from a chunk of primordial solar system material. But earlier observations of 3IATLAS had hinted at something strange: strong nickel emissions with far less iron than expected. The Keck team wanted to map those emissions in detail, to see how the nickel and cyanide distributed themselves around the nucleus, and to understand what that distribution might tell us about the comet's structure and activity. The results were striking. The processed images showed a coma roughly 6,000 kilometers across at the wavelengths observed, with a bright central concentration where the nucleus sits, buried beneath layers of gas and dust. But the coma was not symmetric. The nickel emissions shown in one processed image formed a relatively compact envelope around the nucleus, concentrated but not perfectly round. The cyanide emissions, shown in a comparison image, spread much wider, extending significantly farther from the nucleus in all directions. This difference in spatial extent makes sense if you think about the physics. Cyanide molecules are lighter and more easily accelerated by solar radiation pressure and the expanding gas from the comet's sublimating ices. Nickel atoms are heavier, so they do not travel as far before they either ionize and get swept away by the solar wind, or simply fall back toward the nucleus. The size difference between the two envelopes is not surprising. What surprised observers was the direction. Both the nickel and cyanide showed a bias toward the sunward direction. Remember, comets typically push material away from the sun, forming tails that point in the anti-solar direction. But 3IATLAS, even back in August, when it was still more than 3 astronomical units from the sun, showed enhanced outgassing in the direction of the star. The Keck images made this asymmetry visually obvious. The coma was not evenly distributed. It bulged sunward, and this pattern, first noticed in August, persisted through the October observations from Mars' orbit. It is a consistent feature, not a measurement artifact or a one-time glitch. The comet really does behave this way. Avi Loeb, writing in one of his many Medium blog posts about 3IATLAS, highlighted the Keck observations as further evidence of anomalous behavior. He noted that the sunward bias could be explained by slow rotation or tidal locking, but that such an explanation requires special pleading. Most objects tumble, most comets spin, some rapidly, some slowly, but almost all rotate enough to average out the solar heating over their entire surface. A comet that does not rotate much, that keeps one hemisphere perpetually facing the sun while the other stays cold, is unusual. Not impossible, but unusual. And when you stack one unusual feature on top of another, unusual feature on top of a trajectory with unusual probabilities, on top of a chemical composition with unusual ratios, you start to wonder if unusual is the right word. Maybe the word should be anomalous. Or maybe, and Lobo floats this possibility delicately, the word should be artificial. The nickel emissions deserve special attention because they remain one of the most perplexing aspects of 3IATLAS chemistry. Atomic nickel has been detected in other comets, but always in trace amounts and usually accompanied by iron. The iron-to-nickel ratio in most solar system materials hovers around 10:1, reflecting the relative abundances of these elements in the Sun and in the primordial nebula from which the solar system formed. 3IATLAS does not follow this object is scientifically important as 3IATLAS passes through the inner solar system. You use the best tools available, and JWST is the best infrared telescope ever deployed. Its sensitivity to molecular signatures, its ability to dissect light into exquisite detail, makes it uniquely capable of revealing the chemical composition of distant objects. The observations took only a few hours, but the data they produced would fundamentally reshape our understanding of this comet. The spectrum, spanning wavelengths from 0.6 to 5.3 micrometers, revealed a coma absolutely dominated by carbon dioxide, not just rich in carbon dioxide, dominated. The team, led by Martin Kortener at NASA's Goddard Space Flight Center, analyzed the emission lines and calculated the ratio of carbon dioxide to water in the coma. They found an 8:1 ratio. For every molecule of water sublimating from the nucleus, 8 molecules of carbon dioxide escaped. This is not a minor deviation from the norm. This is a 6 sigma anomaly, meaning it lies 6 standard deviations above the trend for long period, and Jupiter family comets as a function of heliocentric distance. In statistical terms, 6 sigma means the probability of this occurring by random chance. Assuming 3IATLAS is a normal comet, is less than 1 in a billion. You do not get 6 sigma deviations from random noise. You get them when something fundamental is different. To understand why this matters, we need to talk about comet composition. Most comets are dirty snowballs, mixtures of water ice, frozen gases like carbon monoxide and carbon dioxide, organic compounds, and silicate dust. The exact proportions vary, but water ice usually dominates. Water is abundant in the universe. It forms easily in cold environments. It is sticky, meaning it can trap other molecules and dust grains into a cohesive mass. When a comet approaches the Sun and begins to warm, the water ice sublimates first, creating the coma and releasing the dust and other volatiles embedded within it. Carbon dioxide ice has a lower sublimation temperature than water ice, so it starts outgassing farther from the Sun. But there's usually less of it. A typical comet might show a carbon dioxide to water ratio of 1:10 or 1:5 at most. Some comets are carbon dioxide rich, showing ratios approaching 1:1, but those are outliers. Unusual objects that get studied carefully because they deviate from the standard model. 3IATLAS does not just deviate, it obliterates the standard model. 8:1 is off the charts. It is the highest carbon dioxide to water ratio ever measured in a comet. Where do you get so much carbon dioxide and so little water? The simplest explanation is formation location. In a protoplanetary disk, different molecules freeze out at different distances from the star, depending on temperature. Close to the star, it is too hot for anything to condense. Farther out, you hit the water frost line where temperatures drop below about 170 Kelvin, and water ice can form farther still, beyond about 3 or 4 astronomical units, depending on the disk properties. You reach the carbon dioxide frost line where CO2 freezes. Objects that form just beyond the carbon dioxide frost line could, in theory, be rich in carbon dioxide ice with less water, because the water mostly froze out closer in, and the local material is dominated by the more volatile ices. This is a plausible scenario for 3IATLAS. If it formed far from its parent star, in the cold outer regions of a protoplanetary disk, it would naturally be carbon dioxide rich. The composition would be a direct fingerprint of its birthplace. telling us that this comet comes from the deep freeze, the distant reaches where sunlight barely penetrates and temperatures hover just above absolute zero. But there is a complication. The carbon dioxide to water ratio in 3IATLAS is so extreme that it suggests not just formation beyond the carbon dioxide frost line, but something more. Maybe the comet formed in a region with unusually low water abundance to begin with. Maybe the disk was depleted in water, perhaps because it formed from gas that had already been processed in some way, stripped of its lighter molecules by radiation or winds. Or maybe the comet underwent some kind of evolutionary process after it formed, something that selectively removed water while leaving carbon dioxide behind. This is trickier to explain. Water and carbon dioxide have similar volatility, so a process that removes one should remove the other, unless, and this is speculative, the comet has a layered structure. Perhaps the surface is water-poor and carbon dioxide-rich, a result of irradiation by cosmic rays. Over billions of years, cosmic rays can break apart water molecules, liberating hydrogen which escapes into space, leaving behind oxygen that might recombine into other compounds or react with the dust grains. Over time, a surface layer could become depleted in water and enriched in more stable molecules like carbon dioxide. When the comet enters the inner solar system and starts sublimating, we see the composition of that processed surface layer, not the pristine interior. This would mean 3IATLAS is old, very old, possibly older than our solar system. The age question is fascinating. Dynamical models of 3IATLAS orbit, working backward from its current trajectory through the gravitational fields of the Milky Way, suggests the comet has been wandering into stellar space for at least 3 billion years, possibly as long as 14 billion years. The wide range comes from uncertainties in the galactic potential and the unknown history of gravitational encounters the comet experienced. But even the lower estimate, 3 billion years, is ancient. The solar system itself is only 4.6 billion years old, if 3IATLAS is 3 billion years old. It formed during an earlier era of the Milky Way when star formation rates were higher and the chemical composition of the galaxy was different. The thick disk stellar population to which 3IATLAS might belong, based on its velocity and trajectory, consists of old, metal-poor stars, first or second generation objects that formed when the universe was younger, and fewer supernovae had enriched the interstellar medium. A comet formed around such a star would have a different starting composition than a comet formed in our solar system. Lower metallicity, fewer heavy elements, different abundance ratios. The extreme carbon dioxide dominance could reflect that ancient, alien environment. The JWST observations also detected water, carbon monoxide, and carbonyl sulfide in the coma, along with water ice grains and dust. So it is not that water is absent, it is present, just overwhelmed by the carbon dioxide. The carbon monoxide to water ratio, at about 1.4 to 1, is also elevated, but less dramatically so. The carbonyl sulfide OCS is a trace component. Interesting because it is relatively rare in solar system comets, and its presence hints at sulfur chemistry that we do not fully understand. The isotopic composition of the carbon dioxide provided another clue. JWST detected both carbon-12 and carbon-13 in the CO2 molecules, and while the exact ratio is difficult to quantify due to overlapping spectral features, the preliminary analysis suggested it is broadly similar to the ratio found on Earth and in solar system comets. This is significant because it means the carbon in 3IATLAS came from similar nuclear, synthetic processes as the carbon in our own neighborhood. It rules out some of the more exotic formation scenarios, like condensation from molecular clouds with very unusual isotopic signatures. Carbon in this comet is normal carbon, just arranged in an unusual molecular form. NASA's SPIREX mission, a space telescope that observes in the near-infrared with a wide-field spectrum stratoref, independently confirmed the carbon dioxide dominance. In observations made between August 7th and 15th, SPIREX lacks the sensitivity to detect water vapor, but it clearly saw the carbon dioxide emissions and measured a mass loss rate of about 70 kilograms per second. For comparison, typical comets at similar distances from the Sun might lose a few tens of kilograms per second of water. 3IATLAS is losing 70 kilograms per second of carbon dioxide alone, with much less water. The activity level is high, driven by the readily sublimating carbon dioxide ice, which means the comet's nucleus is shedding mass quickly. Over the course of its passage through the inner solar system, it might lose a significant fraction of its total mass, perhaps a few million tons of material. This is not unusual for comets, but it does raise the question of how many prior passages this comet has made through other stellar systems. If it has been wandering for billions of years, has it encountered other stars, undergone other perihelion passages that stripped away outer layers? Is what we're seeing now the core of a once much larger object, a relic worn down by eons of exposure to stellar radiation? The answers remain elusive, but the carbon dioxide dominance offers a hint. This is not a fresh, pristine comet just ejected from its home system. This is something that has survived a long journey, and it carries the scars of that journey in its chemistry. The implications extend beyond 3IATLAS itself. If interstellar comets can have such extreme compositions, then the diversity of planetary systems and the conditions under which comets form must be much greater than we realized. Our solar system might be typical, or it might be an outlier. We have no way to know without more data. The JWST observations of 3IATLAS suggest that comets from the thick disk population from older, metal-poor stars might systematically differ from comets formed around younger, metal-rich stars like our Sun. If true, this opens up a new field of comparative cometry science, using interstellar visitors as probes of the conditions in distant ancient star systems. Each new interstellar object becomes a time capsule, carrying information encoded in its chemistry, waiting for us to decode it. 3IATLAS, with its 8:1 carbon dioxide to water ratio, tells us that at least some corners of the galaxy produce comets unlike anything we have seen before. It tells us the universe is more varied, more creative than our limited sample of solar system objects suggests. But it also deepens the mystery. Why this particular chemistry? Why this particular trajectory? Why this particular moment in human history when our telescopes are finally powerful enough to study such objects in detail? The timing feels almost too convenient, as if the universe is offering us a test, a puzzle designed to stretch our understanding and challenge our assumptions. I do not believe in cosmic conspiracies, but I do believe in the power of coincidence to provoke thought, and 3IATLAS, with its chemical rebellion and its statistical improbabilities, certainly provokes thought. The carbon dioxide discovery from JWST was the piece of evidence that took this object from interesting to extraordinary. It was the data point that made even skeptical scientists pause and reconsider their certainty. Because when you see a 6 sigma anomaly, you have two choices. You can assume you're witnessing a natural but rare phenomenon, the tail end of a probability distribution that extends farther than you expected. Or you can consider the possibility that your model is wrong, that you're not looking at a rare comet, but at something that does not fit the category of comet at all. Most scientists choose the first option. A few choose the second, and the rest of us wait for more data, knowing that the truth, whatever it is, will eventually reveal itself through patient observation and rigorous analysis. December cannot come fast enough. The chemical rebel, JWST's CO2 discovery. August 6, 2025. While ground-based observatories tracked 3IATLAS, and spacecraft at Mars prepared for their October observations, the most powerful telescope humanity has ever built turned its gaze toward the interstellar visitor, the James Webb Space Telescope, positioned at the second Lagrange point, nearly 1 million miles from Earth, oriented its near-infrared spectrograph toward a faint smudge of light moving against the background stars. JWST is not a comet specialist. Its primary mission involves studying the earliest galaxies, probing the atmospheres of exoplanets, examining the formation of stars and planetary systems. But when an object as scientifically important as 3IATLAS passes through the inner solar system, you use the best tools available, and JWST is the best infrared telescope ever deployed. Its sensitivity to molecular signatures, its ability to dissect light into exquisite detail, makes it uniquely capable, revealing the chemical composition of distant objects. The observations took only a few hours, but the data they produced would fundamentally reshape our understanding of this comet. The spectrum, spanning wavelengths from 0.6 to 5.3 micrometers, revealed a coma absolutely dominated by carbon dioxide. Not just rich in carbon dioxide, dominated. The team led by Martin Coordinaire at NASA's Goddard Space Flight Center analyzed the emission lines and calculated the ratio of carbon dioxide to water in the coma. They found an 8-to-1 ratio. For every molecule of water sublimating from the nucleus, 8 molecules of carbon dioxide escaped. This is not a minor deviation from the norm. This is a 6 sigma anomaly, meaning it lies 6 standard deviations above the trend for long period and Jupiter family comets as a function of heliocentric distance. In statistical terms, 6 sigma means the probability of this occurring by random chance is less than 1 in a billion. Assuming 3IATLAS is a normal comet, you do not get 6 sigma deviations from random noise. You get them when something fundamental is different. To understand why this matters, we need to talk about comet composition. Most comets are dirty snowballs, mixtures of water ice, frozen gases like carbon monoxide and carbon dioxide, organic compounds, and silicate dust. The exact proportions vary, but water ice usually dominates. Water is abundant in the universe. It forms easily in cold environments. It is sticky, meaning it can trap other molecules and dust grains into a cohesive mass. When a comet approaches the sun and begins to warm, the water ice sublimates first, creating the coma and releasing the dust and other volatiles embedded within it. Carbon-oxygen ice has a lower sublimation temperature than water ice, so it starts outgassing farther from the sun. But there is usually less of it. A typical comet might show a carbon dioxide to water ratio of 1 to 10 or 1 to 5 at most. Some comets are carbon dioxide rich, showing ratios approaching 1 to 1, but those are outliers, unusual objects that get studied carefully because they deviate from the standard model. 3IATLAS does not just deviate, it obliterates the standard model. 8 to 1 is off the chart. It is the highest carbon dioxide to water ratio ever measured in a comet. Where do you get so much carbon dioxide and so little water? The simplest explanation is a formation location in a protoplanetary disk. Different molecules freeze out at different distances from the star, depending on temperature. Close to the star, it is too hot for anything to condense. Farther out, you hit the water frost line, where temperatures drop below about 170 Kelvin and water ice can form. Farther still, beyond about 3 or 4 astronomical units depending on the disk properties, you reach the carbon dioxide frost line where CO2 freezes. Objects that form just beyond the carbon dioxide frost line could, in theory, be rich in carbon dioxide ice with less water, because the water mostly froze out closer in, and the local material is dominated by the more volatile ices. This is a plausible scenario for 3IATLAS. If it formed far from its parent star in the cold outer regions of a protoplanetary planetary disk, it would naturally be carbon dioxide rich. The composition would be a direct fingerprint of its birthplace. telling us that this comet comes from the deep freeze, the distant reaches where sunlight barely penetrates, and temperatures hover just above absolute zero. But there is a complication. The carbon dioxide to water ratio in 3IATLAS is so extreme that it suggests not just formation beyond the carbon dioxide frost line, but something more, maybe. The comet formed in a region with unusually low water abundance to begin with. Maybe the disk was depleted in water, perhaps because it formed from gas that had already been processed in some way, stripped of its lighter molecules by radiational winds. Or maybe the comet underwent some kind of evolutionary process after it formed, something that selectively removed water while leaving carbon dioxide behind. This is trickier to explain. Water and carbon dioxide have similar volatility, so a process that removes one should remove the other. Unless, and this is speculative, the comet has a layered structure. Perhaps the surface is water-poor and carbon dioxide-rich, a result of irradiation by cosmic rays over billions of years. Cosmic rays can break apart water molecules, liberating hydrogen which escapes into space, leaving behind oxygen that might recombine into other compounds or react with the dust grains. Over time, a surface layer could become depleted in water and enriched in more stable molecules like carbon dioxide. When the comet enters the inner solar system and starts sublimating, we see the composition of that processed surface layer, not the pristine interior. This would mean 3IATLAS is old, very old, possibly older than our solar system. The age question is fascinating. Dynamical models of 3IATLAS orbit, working backward from its current trajectory through the gravitational fields of the Milky Way, suggest the comet has been wandering interstellar space for at least 3 billion years, possibly as long as 14 billion years. The wide range comes from uncertainties in the galactic potential and the unknown history of gravitational encounters the comet experienced. But even the lower estimate, 3 billion years, is ancient. The solar system itself is only 4.6 billion years old. If 3IATLAS is 3 billion years old, it formed during an earlier era of the Milky Way, when star formation rates were higher and the chemical composition of the galaxy was different, a thick disk stellar population, to which 3IATLAS might belong based on its velocity and trajectory, consists of old metal-poor stars, first or second generation objects that formed when the universe was younger and fewer supernovae had enriched the interstellar medium. A comet formed around such a star would have a different starting composition than a comet formed in our solar system. Lower metallicity, fewer heavy elements, different abundance ratios. The extreme carbon dioxide dominance could reflect that ancient, alien environment. The JWST observations also detected water, carbon monoxide and carbonyl sulfide in the coma, along with water ice grains and dust. So it is not that water is absent, it is present, just overwhelmed by the carbon dioxide. The carbon monoxide to water ratio at about 1.4 to 1 is also elevated, but less dramatically so. The carbon disulfide, OCS, is a trace component. Interesting because it is relatively rare in solar system comets, and its presence hints at sulfur chemistry that we do not fully understand. The isotopic composition of the carbon dioxide provided another clue. JWST detected both carbon-12 and carbon-13 in the CO2 molecules, and while the exact ratio is difficult to quantify due to overlapping spectral features, the preliminary analysis suggests it is broadly similar to the ratio found on Earth and in solar system comets. This is significant because it means the carbon in 3IATLAS came from similar nuclear synthetic processes as the carbon in our own neighborhood. It rules out some of the more exotic formation scenarios, like condensation from molecular clouds with very unusual isotopic signatures. The carbon in this comet is normal carbon, just arranged in an unusual molecular form. NASA's SphereX mission, a space telescope that observes in the near-infrared with a wide-field spectrograph, independently confirmed the carbon dioxide dominance. In observations made between August 7th and 15th, Sphere X lacks the sensitivity to detect water vapor, but it clearly saw the carbon dioxide emissions and measured a mass loss rate of about 70 kilograms per second. For comparison, typical comets at similar distances from the Sun might lose a few tens of kilograms per second of water. 3IATLAS is losing 70 kilograms per second of carbon dioxide alone, with much less water. The activity level is high, driven by the readily sublimating carbon dioxide ice, which means the comet's nucleus is shedding mass quickly over the course of its passage through the inner solar system. It might lose a significant fraction of its total mass, perhaps a few million tons of material. This is not unusual for comets, but it does raise the question of how many prior passages this comet has made through other stellar systems. If it has been wandering for billions of years, has it encountered other stars, undergone other perihelion passages that stripped away outer layers? Is what we are seeing now the core of a once much larger object, a relic worn down by eons of exposure to stellar radiation? The answers remain elusive, but the carbon dioxide dominance offers a hint. This is not a fresh, pristine comet just ejected from its home system. This is something that has survived a long journey, and it carries the scars of that journey in its chemistry. The implications extend beyond 3IATLAS itself. If interstellar comets can have such extreme compositions, then the diversity of planetary systems and the conditions under which comets form must be much greater than we realized. Our solar system might be typical, or it might be an outlier. We have no way to know without more data. The JWST observations of 3IATLAS suggest that comets from the thick disk population, from older metal-poor stars, might systematically differ from comets formed around younger metal-rich stars like us. If true, this opens up a new field of comparative cometry science, using interstellar visitors as probes of the conditions in distant, ancient star systems. Each new interstellar object becomes a time capsule, carrying information encoded in its chemistry, waiting for us to decode it. 3IATLAS, with its 8-to-1 carbon dioxide to water ratio, tells us that at least some corners of the galaxy produce comets unlike anything we have seen before. It tells us the universe is more varied, more creative than our limited sample of solar system objects suggests. But it also deepens the mystery. Why this particular chemistry? Why this particular trajectory? Why this particular moment in human history? When our telescopes are finally powerful enough to study such objects in detail, the timing feels almost too convenient, as if the universe is offering us a test, a puzzle, designed to stretch our understanding and challenge our assumptions. I do not believe in cosmic conspiracies, but I do believe in the power of coincidence to provoke thought, and 3IATLAS, with its chemical rebellion and its statistical improbabilities, certainly provokes thought. The carbon dioxide discovery from JWST was the piece of evidence that took this object from interesting to extraordinary. It was the data point that made even skeptical scientists pause and reconsider their certainty. Because when you see a 6 sigma anomaly, you have two choices. You can assume you are witnessing a natural but rare phenomenon, the tail end of a probability distribution that extends farther than you expected. Or you can consider the possibility that your model is wrong, that you're not looking at a rare comet, but at something that does not fit the category of comet at all. Most scientists choose the first option, a few choose the second, and the rest of us wait for more data, knowing that the truth, whatever it is, will eventually reveal itself through patient observation and rigorous analysis. December cannot come fast enough. Fragments, companions, and the extended glow. In late September and early October 2025, A curious pattern emerged on social media and amateur astronomy forums. Multiple observers, mostly using backyard telescopes, and consumer-grade cameras with long exposure capabilities reported seeing something odd in their images of 3IATLAS. The comet itself appeared as expected, a faint, fuzzy patch with a subtly elongation suggesting a coma and perhaps the hint of a tail. But in some images, particularly those stacked from many exposures to increase signal, there seemed to be additional faint sources nearby, not stars. Those were easy to identify and subtract, not cosmic rays or hot pixels. Those showed up as isolated specks and could be filtered out. These were diffuse glows, faint smudges that appeared in the same region of the sky as the comet, but offset by small amounts, as if they were separate objects traveling alongside 3IATLAS. The reports were tentative. Image processing artifacts, scattered light from the comet itself, foreground or background nebulosity that happened to align. Nobody wanted to make strong claims based on data that barely rose above the noise floor. But the reports persisted, and the amateur community started asking whether 3IATLAS might have companions, fragments, or some kind of extended debris field that professional observations had not yet detected. Let me state clearly at the outset, there is no confirmed evidence of co-moving objects or fragments associated with 3IATLAS. None of the professional observations from Hubble, JWST, Keck, or the spacecraft at Mars have reported seeing anything other than the comet itself. If companions exist, they would need to be extremely faint, much fainter than the comet, and positioned in ways that make them hard to distinguish from the background. This is not impossible. Comets can fragment, splitting into multiple pieces that follow nearly identical trajectories for weeks or months before their paths diverge enough to be resolved as separate objects. Comet Shoemaker-Levy 9 famously fragmented into more than 20 pieces before colliding with Jupiter in 1994. Comet Schwassmann. Walkman. 3 broke apart during its close approach to the Sun in 2006, creating a string of mini-comets that spread out along its orbit. Fragmentation is a known phenomenon driven by thermal stress, rotation, tidal forces, or structural weaknesses in the nucleus. An interstellar comet subjected to billions of years of cosmic ray bombardment and the stresses of interstellar travel might be more prone to frag than a solar system comet. So the idea that 3IATLAS could have shed pieces during its passage through the inner solar system is not absurd, but the evidence for it remains circumstantial at best. The extended glow is a different matter. Multiple observations, including the Hubble images from late July, show that 3IATLAS has a coma that extends well beyond what you would expect from a simple point source nucleus surrounded by sublimating gas. The coma appears broad, diffuse, with brightness that falls off gradually rather than sharply. This is not unusual for comets. Many show similar extended structures, but the specific morphology of 3IATLAS has raised questions. Some researchers have noted that the glow appears more symmetric and less centrally concentrated than typical cometary coma. Others have pointed out that the dust distribution seems to lack the usual radial streamers or jets that indicate localized active regions on the nucleus. Instead, the dust forms a smooth envelope, as if it is being released uniformly from the entire surface, or as if it is not dust at all, but something else, some other scattering medium that produces the observed glow. This is where speculation starts to outpace the data, because explanations for an anomalous glow can range from the mundane to the exotic. The mundane explanation is that 3IATLAS has a very porous, fragile nucleus that is disintegrating slowly as it approaches the Sun. Comet nuclei are not solid blocks of ice. They're more like loosely bound rubble piles, aggregates of smaller icy chunks held together by weak gravity and the frozen volatiles acting as glue. As the volatiles sublimate, the structure can weaken and the nucleus can shed not just gas and fine dust, but larger fragments, pebbles, and boulders that drift away slowly and create a diffuse cloud of material around the comet. This cloud, illuminated by scattered sunlight, would produce exactly the kind of extended glow observed. The fact that we do not see individual fragments in the images just means they're too small or too faint to resolve. There could be thousands or millions of small pieces there, each one reflecting a tiny amount of sunlight, collectively creating the smooth envelope we interpret as the coma. This is a perfectly reasonable model, consistent with everything we know about comet physics, and it requires no new physics or exotic materials. The problem is, it also does not uniquely fit the data. Other explanations work equally well, and some of them are more intriguing. The exotic explanation, favored by those who suspect 3IATLAS might be more than a comet, is that the extended glow represents a buffer or shield of some kind. If the object is artificial, if it is a probe or spacecraft, it would need protection from the intense radiation and particle flux near the sun. One way to provide that protection is to surround the craft with a cloud of material, perhaps ice or dust, or even engineered particles that absorbs or deflects the incoming radiation. This buffer would sublime and erode as the craft approaches perihelion, continually replenished from internal reservoirs, creating a dynamic envelope that looks like a comet's coma but serves a different function. From a distance, you could not tell the difference. An artificial buffer designed to mimic cometary outgassing would produce exactly the same observational signatures: gas, dust, a broad glow as a natural comet. Only detailed, high-resolution imaging and spectroscopy might reveal subtle differences, anomalies in the particle size distribution, or the chemical composition that hinted an engineered origin. And those observations are difficult to obtain. Even with our best instruments, the buffer hypothesis is speculative, unsupported by direct evidence, but it is not disprovable with the data we have. It remains in the realm of possibility, a what-if scenario that cannot be ruled out. Avi Loeb has suggested the extended glow might indicate something unusual about 3IATLAS's structure or composition, something that differentiates it from typical comets. He notes that the coma appears more robust and longer-lived than expected for an object at its heliocentric distance. Most comets brighten dramatically as they approach perihelion and then fade quickly as they move away, their activity dropping off once the solar heating diminishes. 3IATLAS showed strong activity even at distances beyond 3 astronomical units, farther from the Sun than the asteroid belt. Temperatures are cold and sublimation rates should be low. The fact that it remained active suggests either a very large reservoir of volatiles, a composition dominated by easily sublimated ices like carbon dioxide, or some internal heat source that drives the outgassing. Even in the absence of direct solar heating, the JWST observations confirmed the carbon dioxide dominance, which supports the second option. But they do not rule out the possibility of an internal heat source. A radioactive decay-powered heat source, for example, could keep the nucleus warm enough to maintain activity far from the Sun. This is not a common feature of natural comets, but it is not unprecedented. Some models of interstellar objects suggest they could contain short-lived, radioactive isotopes incorporated during formation. Isotopes that generate heat through decay and warm the interior over billions of years. Most of those isotopes would decay away. But if 3IATLAS is truly ancient, if it formed in the early galaxy, when supernova rates were higher and the interstellar medium was enriched with fresh nuclear synthetic products, it might contain unusual isotopic compositions that keep it warmer than expected. The companion hypothesis gained traction in part because of a specific observation that went somewhat viral in amateur circles. A Twitter user posting under the handle Night Sky Today shared an analysis suggesting that recent observations showed possible fragments, or co-moving companions traveling alongside 3IATLAS. The tweet was carefully worded. noting the observations were speculative and required confirmation. But it sparked widespread discussion. Other observers began scrutinizing their own images, looking for evidence of additional objects. Some claimed to see faint elongations or asymmetries that could represent fragments. Others saw nothing unusual. The signal, if it exists, is weak and inconsistent, the kind of thing that lives at the boundary between detection and noise. Professional astronomers, when asked about it, generally express skepticism. They note that the sensitivity required to detect faint companions in the vicinity of a bright comet is substantial, and that amateur equipment, while impressive, often struggles with the dynamic range and image processing challenges involved. But they also do not dismiss the possibility entirely. Comet fragmentation is real. If 3IATLAS fragmented recently, say, during its close approach to the Sun, or during some earlier encounter with the stellar system, the fragments could still be nearby, slowly drifting apart, but not yet resolved as separate objects. Future observations might confirm or refute these claims, but for now they remain in limbo, tantalizing but unverified. There is also the question of what a debris field around 3IATLAS would mean for the artificial hypothesis. If the comet is natural in fragmenting, that is, straightforward comets break apart. It happens. But if the comet is artificial, if it is a spacecraft or probe, the presence of debris becomes more interesting. Perhaps the debris is intentional, particles released to create the buffer we discussed earlier. Perhaps it is unintentional damage from micrometeorite impacts during the long interstellar journey. Spacecraft in our own solar system accumulate damage over time. Paint flakes off. Solar panels degrade. Structural components crack and shed small pieces. A probe traveling for millions of years through interstellar space would encounter countless dust grains and gas molecules, each collision chipping away at its surface, eroding its protective layers. By the time it reaches our solar system, it might be surrounded by a cloud of its own debris, fragments and particles that once belonged to the main body but have since separated. This debris, illuminated by sunlight, would create exactly the kind of extended glow we observe. And if you look closely, if you had high enough resolution, you might see individual pieces, larger chunks that stand out against the diffuse background. This is speculation piled on speculation, building a story from hints and shadows. But it is the kind of speculation that keeps people engaged, that keeps them wondering what we might find when we get better data. The reality is that the extended glow and the companion rumors reflect our hunger for mystery, our desire to find something extraordinary in the data. 3IATLAS has given us enough anomalies, enough statistical improbabilities, enough chemical and dynamical oddities, that we are primed to see more. We are looking for patterns. We are looking for clues. And sometimes in our eagerness, we see things that are not there, or interpret ambiguous signals as confirmations of our hopes or fears. This is human nature. It is also how science progresses by pushing the boundaries of detection, by asking whether faint signals might be real, by following up on tentative observations with better instruments and more rigorous methods. The companion hypothesis might be wrong, probably is wrong, but it is worth checking, worth verifying, because if it turns out to be right, if 3IATLAS does have fragments or co-moving objects, that would be scientifically valuable information, regardless of whether the comet is natural or artificial. Fragmentation dynamics, debris evolution, the survival of small bodies in the interstellar medium. These are all topics we understand poorly, and any data we can gather helps refine our models. The December observations will be critical here too, when 3IATLAS reemerges from behind the Sun. Observers will be watching not just for the comet itself, but for anything unusual in its vicinity. If fragments exist, if companions are real, If the extended glow contains hidden structure, those features should become more apparent. As the viewing geometry changes, and as the comet moves into darker sky, away from the sun's glare, high-resolution imaging campaigns are already being planned. Ground-based observatories with adaptive optics, space telescopes with exquisite sensitivity, coordinated observations from multiple sites to build up a comprehensive picture of the comet's environment. These efforts will either confirm the companion hypothesis, showing us a comet surrounded by debris and fragments, or they will put it to rest, revealing nothing but the smooth, unremarkable glow of a slightly unusual but fundamentally natural comet. Either outcome advances our knowledge, either outcome is worth pursuing. And while we wait for those observations, while we wonder about fragments and buffers and extended glows, another revolution is quietly unfolding, one that will transform how we detect and study interstellar objects, one that began with first light from a new observatory on a mountaintop in Chile, Rubin Observatory. The ISO Detection Revolution. June 23, 2025. The Vera C. Rubin Observatory released its first images to the public, and the astronomical community collectively gasped. The images were stunning, not because they showed objects never before seen. Galaxies and nebulae are beautiful but familiar, but because of the sheer scale and detail captured in such a short time, a mosaic of the Trifid and Lagoon nebulae, compiled from 678 separate images taken over just 7 hours, revealed clouds of gas and dust in exquisite detail. Faint structures invisible to smaller telescopes suddenly rendered in vivid clarity. A video panning across a tiny fraction of the sky showed approximately 10 million galaxies, each one an island universe containing billions of stars. And that was just 0.05% of what Rubin will observe. Over its 10-year mission, the numbers were staggering. In roughly 10 hours of the commissioning observations, Rubin discovered 2,104 previously unknown asteroids, including 7 near-Earth asteroids that posed no threat but had gone unnoticed by every other survey. Annually, all other ground and space-based observatories combined discover about 20,000 asteroids. Rubin, in its first day of serious work, found 10% of that annual total. This is not an incremental improvement over existing capabilities. This is a revolution. The Rubin Observatory sits atop Cerro Pachon in Chile, a 27-meter peak in the Andes, chosen for its clear, dark skies and stable atmospheric conditions. The observatory houses the Simoni Survey Telescope, an 8.4-meter instrument with an unusual design, optimized for wide-field imaging. Unlike traditional telescopes that focus on small patches of sky, at high magnification, the Simoni telescope captures enormous swaths in a single exposure, 7 full moons wide, with a field of view covering nearly 10 square degrees. This is made possible by the largest digital camera ever built for astronomy, the LSST camera, a behemoth weighing 3 tons and containing 3.2 gigapixels across an array of charge-coupled devices, cooled to minus 100 degrees Celsius. Each image. The image from this camera is so detailed, it would require over 400 ultra-high-definition television screens to display at full resolution, and the telescope takes these images constantly, night after night, mapping the entire visible southern sky every 3 to 4 days. Over the course of a decade, Rubin will observe each patch of sky hundreds of times, creating a time-lapse movie of the universe in unprecedented depth and cadence. For interstellar object detection, Rubin is a game-changer. The problem with finding interstellar visitors has always been speed and rarity. These objects move fast, often tens of kilometers per second relative to the solar system, and they are faint, reflecting very little sunlight because they are small and dark and far away. By the time you discover one, calculate its orbit, and realize it is interstellar. It might already be leaving, shooting past the sun and back into the void before you can study it properly. This happened with 1I. By the time astronomers recognized it as interstellar, it was too faint and too distant for detailed observations. 2I Borisov was luckier, discovered farther out and tracked for months, but still the observation window was limited. 3IATLAS was discovered relatively late in its approach, giving us only a few months to prepare campaigns and coordinate observations. Before perihelion, we need earlier detection. We need to find interstellar objects when they are still far from the sun, when we have time to plan, to mobilize resources, to perhaps even send a spacecraft if the object is interesting enough and the trajectory favorable. Rubin will provide that early detection. The observatory survey strategy, called the Legacy Survey of Space and Time, or LSST, involves repeated observations of the same regions of sky separated by days or hours. This allows Rubin to detect anything that moves or changes: asteroids, comets, variable stars, supernovae, transient events of all kinds. Software algorithms compare each new image to previous images of the same region, identifying objects that have shifted position or altered brightness. For solar system bodies, this motion detection is straightforward. Asteroids and comets move against the background stars in predictable ways, and their angular motion across the sky tells you roughly how far away they are and how fast they are traveling. Interstellar objects move differently. They come in on hyperbolic trajectories, with velocities high enough to escape the sun's gravity, and their motion across the sky can be faster than typical solar system objects. This makes them harder to detect with traditional surveys that assume objects move slowly and follow predictable orbits. But Rubin's cadence and coverage are designed to catch these fast movers. The machine learning algorithms being developed specifically for LSST data include classifiers, trained to recognize interstellar object candidates based on their motion characteristics, distinguishing them from the thousands of asteroids and comets that clutter the inner solar system. Estimates vary, but most models predict Rubin will discover between 1 and 70 interstellar objects per year, once it reaches full operational capacity. The wide range reflects uncertainties in the population density of these objects in nearby interstellar space. We know 1I was discovered, and from that single detection, we can infer a rough density, about 0.1 object per cubic astronomical unit at any given time. But that number is highly uncertain. It could be 10 times higher or 10 times lower, and we would not know until we get more detections. If the density is on the high end, Rubin could find dozens of interstellar visitors every year. If it is on the low end, we might see only a handful per decade. Either way, within a few years, we will have a real sample. Not 3 objects, but 30 or 300. Enough to start doing statistics. Enough to understand the range of compositions and trajectories and properties these visitors exhibit. We will learn what is common and what is rare. We will learn if 3IATLAS is an outlier or representative of a significant population, and we will have opportunities, many opportunities, to study interstellar objects in detail, to launch dedicated missions, to perhaps even rendezvous with one and bring samples back to Earth. The detection of 3IATLAS itself provides a tantalizing preview of Rubin's capabilities. Although the official discovery came from the Atlas survey on July 1st, Rubin had actually imaged the comet 10 days earlier on June 21st. During its commissioning phase, the images were archived but not immediately analyzed because the observatory was still calibrating its systems and testing its data pipelines. When the Atlas discovery was announced, Rubin's team went back through their archives and found the comet, sitting right there in their data, a faint smudge moving slowly against the starfield. This pre-discovery detection is significant because it shows Rubin can find interstellar objects, even before they are officially recognized. even when they are still faint and far from the sun. Once the observatory is fully operational and the automated detection algorithms are running in real time, such objects will be flagged immediately, within hours of observation, giving the astronomical community maximum time to respond. This could be the difference between a brief glimpse and a thorough investigation, between missing critical data and capturing a complete portrait of an interstellar visitor. Rubin also observed 3IATLAS multiple times through early July, collecting 37 images in R, E, and Z band filters. These observations provided high-precision measurements of the comet's position and brightness, with typical astrometric accuracy of about 20 milliseconds and photometric precision of about 10 millimagnitudes. From these measurements, the Rubin team derived an improved orbit and calculated the comet's absolute magnitude, a measure of intrinsic brightness that allows you to estimate its size. They found an absolute magnitude of 13.7, which translates to an effective nucleus radius of about 5.6 kilometers, assuming a standard albedo. This is consistent with other estimates from Hubble and ground-based observatories, confirming that 3IATLAS has a nucleus several kilometers across, large enough to be a substantial body, but small enough to be easily perturbed by non-gravitational forces if they exist. The Rubin data also showed no evidence of photometric variability on hourly timescales, meaning the comet's brightness did not flicker or change rapidly as it rotated. This supports the earlier inference that C-ATLAS rotates slowly, if at all, consistent with the sunward biased outgassing pattern. The broader implications of Rubin's capabilities extend beyond just finding interstellar objects. The observatory will also revolutionize our understanding of the solar system's small body populations, discovering millions of asteroids, tens of thousands of Kuiper Belt objects, countless comets, and potentially even a ninth planet if it exists in the outer solar system. Every night, Rubin will detect roughly 10 million changes in the sky, transient events ranging from explode-shooting stars to asteroids shifting position, to galaxies flaring as their central black holes devour material. Processing this flood of data requires sophisticated algorithms and massive computational resources. Rubin will generate about 1 petabyte of data every 10 days, more than 60 petabytes over the 10-year survey, an amount of information equivalent to everything ever written in any language in human history. Managing this data, analyzing it, extracting meaningful signals from the noise represents a challenge on par with building the telescope itself, but the payoff will be transformative. Rubin will give us a dynamic view of the universe, showing us not just where objects are, but how they move and change over time. And for interstellar objects, that dynamic view is exactly what we need. There is also the tantalizing possibility of using Rubin data to identify interstellar objects that could be targeted by spacecraft missions. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, is designed to wait at the second Lagrange point, the same location where JWST orbits, until an interesting target appears. Once a suitable comet is identified, Comet Interceptor will leave its parking orbit and chase it down, conducting a flyby with multiple probes to study the comet from different angles and distances. The mission was conceived with long-period comets in mind, objects making their first visit to the inner solar system and therefore relatively pristine. But it could just as easily target an interstellar object. If one appears at the right time with the right trajectory, Rubin's early detections will be crucial for identifying such targets. If the observatory finds an interstellar visitor while it is still several astronomical units from the Sun, mission planners will have months or even years to calculate intercept trajectories and prepare the spacecraft. The Delta-V requirements for intercepting an interstellar object are steep. These things move fast, but not insurmountable if you have enough lead time. Comet Interceptor might get its chance to study an object like 3IATLAS or perhaps something even stranger, something that does not fit cometary models at all. The statistical studies enabled by Rubin's discoveries will also help settle some of the debates surrounding 3IATLAS. Is its trajectory really as improbable as it seems? Or does it fall within the natural range of variation? Is the carbon dioxide dominance a fluke? Or do many interstellar comets from the thick disk population show similar chemistry? Is the nickel emission pattern unique or common among objects formed in metal-poor environments? These questions cannot be answered with a sample size of 3. They require dozens or hundreds of detections, and Rubin will provide them within 5 years, perhaps sooner. If the interstellar object population density is on the high end of the estimates, we will have enough data to draw firm conclusions. We will know if 3IATLAS is anomalous or typical, and if it turns out to be anomalous, even within a large sample, if its properties remain outliers. No matter how many interstellar objects we discover, then the artificial hypothesis gains weight. Not proof, but weight. Enough weight to justify more serious investigation. Perhaps even dedicated missions to study such objects up close and determine once and for all what they are. For now, Rubin has opened a new era. The era of routine interstellar object discovery is beginning, and with it comes the promise of answers to questions we've been asking since we first looked up at the night sky and wondered what lies beyond our cosmic neighborhood. 3IATLAS may be the last interstellar visitor to arrive in obscurity, discovered by accident and studied in haste. Future visitors will be expected, anticipated, tracked from the moment they cross into the solar system, and that changes everything. The controversy, science versus speculation. The debate over 3IATLAS has split the astronomical community in ways that few objects have managed to do. On one side, you have researchers like Avi Loeb, the Harvard astrophysicist who has never been shy about proposing unconventional ideas, arguing that the cumulative evidence warrants serious consideration of the artificial hypothesis. On the other side, you have the majority of professional astronomers who insist that while 3IATLAS is unusual, it remains within the bounds of natural phenomena and does not require invoking extraterrestrial technology. The divide is not just about interpreting data, it is about how science should approach extraordinary claims, about the balance between open-minded inquiry and skeptical rigor, about what counts as evidence and what counts as speculation. And it is played out very publicly in academic papers, blog posts, social media threads, and conference presentations, making 3IATLAS one of the most polarizing objects in recent astronomical history. Havelock's position is nuanced, at least in his own telling. He does not claim 3IATLAS is definitely artificial. He says the probability is significant, somewhere around 30 to 40% based on his assessment of the various anomalies, and that this probability is high enough to justify treating the artificial hypothesis as a serious scientific possibility, rather than a fringe idea to be dismissed out of hand. His argument rests on cumulative improbabilities, the 5-degree ecliptic alignment with 0.2% odds, the triple planetary close approach with 0.005% odds, the 8-to-1 carbon dioxide to water ratio that sits 6 sigma above the norm, the nickel emissions without corresponding iron, the sunward biased outgassing. Any one of these features taken alone could be explained as a rare but natural occurrence. But when you multiply the probabilities, when you stack low odds on top of low odds, the cumulative likelihood of all these features appearing together in a natural object becomes vanishingly small. At some point, Loeb argues, you have to consider the alternative explanation that these features are not coincidences, but design choices, indicators of intelligence and engineering rather than random cosmic accidents. The mainstream counterargument focuses on sample size and the problem of post hoc reasoning. With only 3 confirmed interstellar objects, we have no baseline for what is normal. We do not know the typical range of trajectories, compositions, or behaviors for objects from other star systems. Maybe 5-degree inclinations are common because of some dynamical pathway we have not yet identified. Maybe carbon dioxide-rich comets are abundant in the thick-this population, reflecting different formation conditions billions of years ago. Maybe nickel emissions without iron are a signature of specific mineral phases that we rarely see in solar system comets, but are common elsewhere. Until we have a larger sample, we cannot judge what is anomalous and what is simply unfamiliar. The post hoc reasoning problem is equally important. If you look at any object with enough scrutiny, you will find features that seem unusual or improbable. The human brain is wired to see patterns and meaning in randomness, to construct narratives that explain coincidences. 3IATLAS has received intense scrutiny precisely because it is interstellar and therefore interesting. If we applied the same level of analysis to a random solar system comet, we would probably find comparable anomalies, unusual chemical ratios, or unlikely trajectory alignments that could be spun into mysterious stories. The difference is that nobody bothers to look that closely at ordinary comets. The anomalies of 3IATLAS may simply reflect observation bias. We are looking harder, so we are finding more things that seem strange.